Our next talk is also a 5-minute talk. We have Pawel. Go ahead.
Hello. So humans are remarkably agile. We move in such a way that we're really good at rapidly changing directions and repositioning our limbs. Studying agility allows us to better understand the neuromechanical mechanisms that enable it and the factors that limit it. Maximum height vertical jumping is a good entry point to study agile motion. In maximal height vertical jumping, the objective is unambiguous. You want to maximally redirect your center of mass. So if we think of the body as a point mass and the musculoskeletal leg as this force actuator without a mass, when you extend your legs, your center of mass goes up. So if we think of this actuator as ideal, the force is not limited by the speed at which the actuator goes up, and the force is not limited by the range of the extension. This means that with an increasing squat depth, there's an increase in jump height, which means that the deeper you go, the higher you jump. Realistically, the mechanical characteristics of our leg do not work like this. The purpose of our work is to identify the actuator characteristics of the leg, to determine how the leg actuator characteristics limit jumping performance relative to an ideal actuator, and given the identified actuator, determine whether people use an optimal coordination. So in our model, we defined this force-velocity relationship in the leg actuator such that when the actuator velocity increases, the actuator force goes down. And the unknown parameters are this Fmax, which is the optimal isometric force, and Vmax, which is the maximum velocity at zero force. Additionally, we consider this inverse parabolic force extension relationship such that there's an optimal operating length, and at regions away from that optimal operating length, the force goes down. And our unknown actuator characteristics are this optimal operating length and the parabolic width. These actuator properties are modeled from known muscle mechanical characteristics. In our model, we consider simple activation dynamics, and we couple this with the movement dynamics of a point mass working against gravity. And so what we get is a differential equation that has 4 unknowns, and it predicts jump height as well as ground reaction forces. So we have our model, and we have our 4 unknown parameters. To determine these parameters, we have human subjects jump on an instrumented treadmill. They perform maximum vertical squat jumps. 30 jumps are performed at randomized initial but controlled depths using a simple apparatus. And 20 jumps are at self-selected depths. And the outputs from this are the vertical ground reaction forces. We perform a least squares optimization to optimize the model predicted ground reaction forces to match that of the empirical data. So this optimizes until it converges on an optimal. And we do this for each individual jump, so there's 500 optimizations. And what we find in the end is that the model predicted ground reaction forces match well with the empirical data with an R² value of 0.9, giving us confidence in the model to predict ground reaction forces. And from this, we predict our actuator characteristics. So we identify the actuator characteristics, so the Fmax and Vmax, and as well as the range of velocities that people experience during a jump. So what we find is that Fmax is about 6 times body weight, and Vmax is about 1.4. To get a better intuition on the Vmax, we look at the range at which people are operating at. And as you can see, they're at a point where they're losing a lot of force compared to the ideal actuator because of this relationship. We also identify the force extension parameters, so the ideal operating length, and the parabolic width, as well as the range at which people operate at. So we identify these parameters within a biomechanically feasible range and with low variability. So coming back to the ideal actuator, looking at the squat depth versus jump height, our model predicts this plateau as squat depth increases. And indeed, this is what people do, showing our empirical data. So comparing the model predicted jump height, here at the end, to an ideal actuator, we see a 4-fold difference between the achievable jump height of the model and the ideal actuator. If we were to remove the force extension characteristics of the model, we see a little bit of an increase in the achievable jump height. And if we were to remove the force velocity characteristics, we see a major increase in jump height potential. This suggests that the force velocity characteristics of the actuator greatly limit its performance. So they're able to achieve a higher jump without this. Finally, looking at the experimental data that with the self-selected conditions, we see that people choose a strategy that optimizes the characteristics of their actuator. So they're jumping at the optimal here. I have a poster upstairs that has more details of this model, and I'd love to chat more about it. Thank you.
All right, we have time for a question or two.
So it seems like people are performing at the peak of that curve, but it also seems like a fairly shallow peak. That guy, yeah.
Over here?
Yeah. Do you have any comments on, what, if we find that peak, I mean, are we sensitive to those small variations considering how shallow it is?
You mean over here? Are we sensitive? Okay, yeah.
The little green dots. Those
Yeah. So what I found is that what people tend to do is, since it's really low sensitivity to the jump height there, there's quite a large variation in the depth that they choose, and I think this is because there's a really small difference in jump height. So there's this variability that is okay because the jump height isn't higher.
Right.
So.
Art?
I'm just curious, I would have expected it to be hard to get this data well, because I would expect subjects to cheat, meaning you ask them to do this squat depth, and I'd expect them to cheat by squeezing in whatever counter movement they can get away with. So you didn't see that?
So if I did see that, it would be obvious in the ground reaction force, because if they're doing a counter movement, they would decelerate downwards. So for those trials, I omitted those trials.
How badly did you have to, correct them?
People got it after a couple, like the first 3 or 4 jumps, they kind of learned. And then it was pretty easy. I had a very simple apparatus that you kind of just touch. It was like a very soft rod. But for the self-selected conditions, there was no problem at all. So they were instructed to just go down, hold it at 0 velocity for about 1 second, and then jump as high as they can.
Andy?
You have no series elastic spring, and you don't think it makes any difference?
I have no series elastic spring.
And you don't think it makes a difference?
I'm not sure. I didn't look into that.
Okay, last question is back here.
Did you do anything to account for fatigue in subjects, because maximal squat jumps are hard, and you did like 30 to 60 of them?
They did 50 jumps. Yeah, so what I didn't say here is that there was like a significant rest period too. So they would jump approximately 5 to 10 times and take a rest. And then between the 30 and 20 jumps, there was like a longer rest. Yeah. Okay, thank you.
Okay, let's thank Pawel.
Disappointed.